Doppler effect and its applications. Have you ever heard a police car, ambulance or fire engine pass and heard the siren change suddenly? Based on many observations, an Australian physicist and mathematician, J.C. Doppler, proposed the Doppler effect in 1842. According to him, the Doppler effect is the shift in frequency and wavelength of waves which emitted from a source moving with respect to the medium, a receiver moving respect to the medium, or even a moving medium. In this image, we have a ball. Let's pretend it's a fire engine. The fire engine is about to start sounding its siren in a minute. We can see the sound waves propagating towards from the source. This is the sound wave created by the siren. As you can see, it travels in all directions equally. As a result, any observer on any side of the fire engine would hear the exact same sound because the wavelength and frequency is the same in all directions, as the sound waves are coming from a stationary source. The wavelength is the distance from the crest of one wave to the crest of the next. It can also be true to true. The frequency of a wave is the amount of waves that pass a given point in 1 second. In the case of this video, it is about one wave every 2 seconds. In order to understand the Doppler effect, let's see how wavelength, frequency and pitch are related. We already know that the frequency of the waves in this video are about 1 every 2 seconds. But watch what happens to the wavelength when the frequency of the waves is increased to 4 every 2 seconds. Speed the siren up by 2. So, if you double the frequency of a wave, you halve its wavelength. Next up is the relationship between frequency and pitch. It's quite simple. All it says is that the higher the frequency of a wave, the higher the pitch will be. High frequency is equal to high pitch and low frequency is equal to low pitch. So, the relationship between all three is high frequency equals short wavelength equals high pitch. Low frequency equals long wavelength equals low pitch. Now, we can understand the Doppler effect. The Doppler effect explains what happens when the object that is creating the sound begins to move. This time, we will watch the sound waves with the siren muted. As you can see, the sound waves are bouncing up towards the front of the moving object. They are also growing further apart at the back of the moving object. This means there is an apparent change in the frequency and wavelength of the waves at the front of the object. There is also an apparent lowering of the frequency and wavelength of the waves at the back of the object. The object is still producing the same amount of sound waves, but its motion is making the frequencies and wavelengths to change at the front and back of the object. So, what would this change in frequency do to the sound heard at the front and back of the object? As we already know, the higher the frequency, the shorter the wavelength, and the higher the pitch. And the longer the frequency, the longer the wavelength, and the lower the pitch. Examples of Doppler effect. Now, let's see an example for the application of the Doppler effect. Consider an ambulance speeding past to you. The pitch of the siren increases as the ambulance approaches you, and the pitch decreases when the ambulance moves away from you. There is a similar apparent change in the pitch of the sound heard when the source of the sound is addressed and the listener moves towards or away from the source. The change in pitch is due to a shift in the frequency of the sound waves. Doppler effect is observed in light also. Suppose a star resists from Earth then the frequency of the light emitted by the star decreases or wavelength increases. Thus, the spectral lines are shifted towards the red end of the spectrum. This is called red shift. Similarly, when star moves towards the Earth, the spectral lines shift towards the blue end of the spectrum. Applications of the Doppler effect. 1. Define the velocity of the speeding car. Let us see how a traffic police catches speeding motors. Short waves emitted from an observation center are directed towards the speeding vehicle. These waves are reflected by the car to the observation center. By calculating the shift in the wavelength, the velocity of the speeding car can be determined. To determine the depth of oceans, we can apply the Doppler effect for estimating the depth of oceans. For this, we make use of sonar. A transmitter from a ship transmits sound waves towards the ocean floor. These waves are then reflected by the ocean floor and are received by the receiver. Note the time taken by the waves to come back to the source. Now, we can estimate the depth of the ocean by using the formula D is equal to V multiplied by T by 2, where V is equal to velocity of the sound waves and T is the time taken. To calculate the speed of astronomical bodies, the Doppler effect of light can be used to measure the speed of stars and galaxies. The spectrum of lights coming from the planets and stars are photographed over a long period. By observing the Doppler shift, one can conclude whether they are moving towards or away from the Earth. To study Saturn's rings. Concentric rings surround the planet Saturn. These rings reflect light and are not self-luminous. The Doppler shift of light reveals that the rings are not continuous, but they consist of many particles.